Hi students, in this video we're going to talk about concentrations. Now, concentration is the amount of solute in a certain amount of solutions. And we have quite a few different ways of expressing the amount of our solute in our solution. And some of them are molarity, mass, volume, percent, percent by mass, percent by volume, parts per million, parts per trillion. Oops, I skipped parts per billion. And there's probably 100 other ones, but we're going to go through the most important ones in the next few sections. Now, remember that a solution includes the solute, the thing that's being dissolved, and the solvent, the thing that's doing the dissolving. And if we have more solute in our solution, we are going to be more concentrated. And if we have less solute in our solution, we're going to be less concentrated, or we can say we're more dilute, or that's the dilute solution right there. Now, the most common measure of concentration in chemistry is molarity. And molarity is moles of solute over volume of solution, and that's in liters. So it's not M, that would be mass. It's moles over liter. And we can see that right down here. Moles over liter. Now, moles over liter, how we can also symbolize that is with a big M. And you'll see that right here, and you'll see that right there. So you can use those two things interchangeably, mole over liter or the big M, which just means mole over liter. Okay, so it's the number of moles of our solute that are dissolved in 1 liter of solution. So it doesn't matter what your solute is. It could be NaCl, which is sodium chloride, or potassium bromide, or like we see over here, potassium hydroxide. It's telling us how many moles are in that 1 liter of solution. And if that number right there is larger, then we have more solute in that solution, and the solution is more concentrated. So what that is saying right there, that 0.80 big M of potassium hydroxide, that's saying that you have 0.80 moles of potassium hydroxide in every 1 liter of that solution. And the other way that we can write that is 0.80, and then the moles over liter is the big M, and we have the solute there, KOH, and you'll see exactly what I just wrote right there. Right there. Okay, so we have 0.80, and we say molar, not molarity. I don't know where the ITY went, but that's how we say it in chemistry. 0.80 molar potassium hydroxide solution. Again, we don't say 0.80 molarity potassium hydroxide solution. I don't know where that came from, but we're humans and we tend to be lazy and shorten things, so that's how we say it. That bottle is a 0.80, and we say molar potassium hydroxide, and then we say solution. That's how you would say it in English if you're standing in the stockroom looking for the bottle of that stuff. So this right here, that would be a 0.08 molar potassium chromate solution. And you always have to say what the solute is. And if we don't specify what the solvent is, we assume that it's water. Now, the solvent isn't always water, but if it doesn't say what it is, then we assume it's water. Now, looking down here at the bottom at 3 different solutions of sodium chloride, what we'll notice is the first one we have 0.5 molar, The second one is 1.0 molar, and the third one is 1.5 molar. And from the pictures, you can see that going from left to right, you have more and more of your solute, the sodium chloride, in that solution. And that is why the molarity, or the concentration, of these solutions is increasing there. So this is the concentrated solution of this series, and this would be the dilute solution in that series of those three. All right, so how do we prepare a solution in the lab? Well, what you would do is you do a calculation to figure out how much of your solute you'd need to measure out. And I'll show you guys how to do that calculation in a little bit. But we're going to measure out a certain amount of our solute on the balance, and then we're going to go ahead and pour it into this funny looking flask thing. This is called a volumetric flask. And the volumetric flask has a little mark up there that indicates a certain volume. And usually on the volumetric flask, it'll tell you what the volume is. So it'll say 250 milliliters, or it'll say 1 liter, or 500 milliliters, whatever it is. Okay, so what you do is then you go ahead and you pour your solute into the bottom of your volumetric flask there. And then you get a bottle of deionized water. So we have DI water. And we squirt it into the beaker to get any of the remaining solute particles that are in there and get them down into the volumetric flask. And then you're already filling up the volumetric flask with your DI water, and that's good. You're starting to make your solution. And at this point, you'd give it a little stir, or some books will say give it a swirl. So you'd pick it up and swirl it around so that your solute particles would dissolve into your water. And then you would keep on filling it up, and at this point you'd give it another swirl, and you'd keep on filling it up with DI water until the meniscus reaches that little mark right there. And that's telling you that you have made that certain volume of solution. So if this volumetric flask said 250 milliliters on it, that would mean that you had made 250 milliliters of your solution. And in this case, it's sodium carbonate. So we would have made 250 milliliters of a sodium carbonate solution. Now, in order to know what the concentration or the molarity of that solution is, we would have had to know how many grams of sodium carbonate we put in there and go ahead and do a calculation. Now, I wanted to point out at the very beginning, the A and B steps, some people like to take the beaker off of the balance and go ahead and squirt some DI water into the beaker at that point to just start making a slurry, start dissolving it, and then go ahead and pour it in there after they've started to dissolve it. You'll see that in pictures too. That's fine. That's just a different way of making a solution. Now, another thing I wanted to point out is you did not squirt 250 milliliters of DI water into your 250 milliliter volumetric flask. You put less than 250 milliliters of water in there. You made 250 milliliters of solution, but you didn't add 250 milliliters of water. And why do you think that is? Why do you think you added less than 250 milliliters of water in here? Well, our solute down here takes up space. So it takes up a certain amount of volume. So you have the solute taking up volume and you have the water taking up volume, and together they take up 250 milliliters of space. If you had the solute down there and you added in 250 milliliters of water, you would have greater than 250 milliliters of solution, because you'd have the 250 milliliters of water plus whatever volume your solute takes up. So that's how we would make a solution in the lab. All right, so that means we have to do some math. I know you guys love it though. So here we go. You dissolve 5.66 grams of potassium bromide in enough water to make 27 milliliters of solution. Now notice the problem says in enough water to make 27 milliliters of solution, and not you took 5.66 grams of potassium bromide and added 27 milliliters of water. That's not what you did. You made 27 milliliters of solution total, okay? So it says, what is the molarity of your solution? And the molarity, remember you guys, that is one form of concentration, and it's one that we use all the time in chemistry. And molarity is moles of solute over liters of solution. So that says SOLN period. So it's short for solution. So we need to change grams of our solute into what? Into moles. And we have a volume over here, 27 milliliters, and we need to change milliliters into what? Into liters. And we know how to do both of those. So we'll go and remember, we're going to let our units guide us, and we want to get rid of grams, and we want to go where? We want to go to moles. And if you're relating moles to grams or grams to moles, you're using what kind of conversion factor? You're using a molar mass. Now, where do I get the number that goes in the bottom next to grams? I get it right off of the periodic table. I pull out my periodic table and I add up the mass for potassium and I add up the mass for bromine, and I get 119.0. Now notice how you have 3 sig figs in your original given. So with your conversion factors, convention states that you usually would like to go 1 more sig fig. If you can only go the same amount of sig figs, okay, but you don't want to go less. All right. So right there, we do the calculation, 5.66 divided by 119, and we're going to get 0.0476, 3 sig figs, moles of potassium bromide, and are we done? No, we need to get liters, and then we need to divide moles by liters. All right, so we can get to liters from milliliters, so we're going to go ahead and put the other we're going to put the other given there and then write a conversion factor. Letting our units guide us, we know that we need milliliters on the bottom because milliliters divided by milliliters is what? Is 1, and we're trying to get to liters. And at this point in the semester, we should know that in 1 liter, you have 1,000 milliliters, and those milliliters cancel out. So we have 27 divided by 1,000, and that's going to give us 0.027 liters. So now we can put those two things together, and we have 0.0476 moles of potassium bromide divided by 0.027 liters, and what we're going to get is 1.76 moles of potassium bromide over 1 liter. And then we should say to ourselves, wait a minute, this value down here only has 2 sig figs. So I need to go to 1.8 to have the correct number of sig figs. And also, moles divided by liters right there is what? How else can we write it that takes up less space? We can write it as the big M, and we always want to put what our solute is. And that, my friends, would be the answer right there. And if that label was on a bottle, you would say, I've got the 1.8 molar potassium bromide solution. How you can also write it is like this: 1.8 mole per liter KBR, okay? Because the big M is exactly the same thing as mole per liter. This value that we wrote right there, the 1.76 mole of potassium bromide over 1 liter, another version of that would be mole per liter potassium bromide. I'm just showing you different ways that you will see the exact same thing, okay? And make sure you have the correct sig figs on that. Okay, so we're going to dissolve 2.45 milligrams of copper 2 sulfate in enough water to make 55 milliliters of solution. And we want to know what our concentration is. And the only concentration that we have done so far is molarity, so we're going to assume that's molarity. Okay, so usually we go grams to moles, but this time we have milligrams. Can we get to moles? Yes, we can, because we know how to go from milligrams to grams. And how many milligrams are in a gram? 1,000. Okay, so milligrams cancels out. And I forgot to write my copper sulfate up here. Bad teacher, bad. And what I'm going to do next is get rid of grams and go where? To moles. So 1 mole of copper 2 sulfate is how many grams? Where would I get that number? Off the periodic table. I'd pull out the periodic table and I'd say, okay, an oxygen weighs 15.999. I've got 4 oxygens, so 15.999 times 4 plus whatever sulfur weighs plus whatever copper weighs. And what we're going to get on that one is 159.6. And then we're going to do the calculation on that, and we're going to get 0.0000, so that's 4 zeros, 154 moles of copper 2 sulfate. And I keep saying copper 2 sulfate because remember, copper is one of those transition metals that has a variable charge, so sometimes it's +1 and sometimes it's +2. But if you only have one of them and it's pairing with sulfate, that one copper has to be +2 because sulfate, SO4 minus, is always -2. And the charges have to balance. They have to add up to 0 because a neutral compound is a happy compound. So if sulfate's -2, then that cation, that copper right there, has got to be +2. So it's a copper 2 sulfate. All right, and then we want to know the volume. So we have 55 milliliters, and we've got to get that to what? We have to get that to liters, and liters is the bigger unit. And how many milliliters can we get in a liter? Again, 1,000. So what we have here is 0.0555 liters. And we're going to put those two things together and we're going to find our molarity. So we have 0.0000 0.154 moles of copper 2 sulfate divided by 0.0555 liters. And what we're going to get with 3 sig figs on the top and 3 sig figs on the bottom is 0.000277. And we can write mole per liter copper sulfate, or the other way that we can write that is like this. Mole per liter is also what? The big M, exactly the same thing. And how you would say that if this was on a label on a bottle is I've got a 0.000277 molar copper 2 sulfate solution. Alrighty, on to problem 3. If you have 60 milliliters of a 0.988 molar sodium chloride solution, how much sodium chloride did you start with? So it's asking you, how much sodium chloride did you put on the balance? Like, what did the balance read for you? How many milligrams or how many grams? So this one isn't straightforward, where we calculate for moles and we calculate for liters and we put moles over liters, and there we go, there's the concentration. What it's giving you is it's giving you the volume and it's giving you the concentration, the molarity. So before we had the moles and we had the volume, and we did moles divided by volume to get the concentration, to get the molarity. But now we don't have the number of moles, which means we don't have the number of grams. We're given the concentration instead. So we have to work this one a little bit differently. So you're given two givens. You've got 60 milliliters and you've got 0.988 molar sodium chloride. When you're given a volume and you're given a molarity, start with the volume. You want to save your concentration to use as a conversion factor. And what on earth I mean, I will show you. Just remember to start with your volume. Okay, so we've got 60 milliliters. And when we have milliliters and we're working with concentration, we're going to want to switch that to what? We're going to switch it to liters. So you're going to have milliliters on the bottom and you're going to have liters on the top. So liters is the bigger unit. So we're going to put the 1 next to it. And then we're going to say how many milliliters can we fit in that liter. And it's the same as it always is. There's 1,000 milliliters in a liter. So we cancel that out. We cancel the milliliters out. And, oops, hold on. I didn't mean equals there. Let me erase that. Okay. And now we're in liters. And we need something that cancels out liters and gets us to moles, because if we have moles, then we can get to grams. And the balance displays in grams. And we don't have any other piece of information except for the molarity, so we're going to have to figure out how we're going to use that. And what we can do is change this right here back into moles per liter. And what that looks like is this, 0.988 moles of sodium chloride divided by 1 liter. This, what I just wrote right here, is exactly the same as this right here. We just wrote it differently. And that will allow us to cancel out the liters. Yay! And now we're in units of what? We're in moles. And that's good because we know how to go from moles to what? Grams. And grams are what we want here. All right, so we have 1 mole of sodium chloride on the bottom there because we're letting our units guide us and we want to get rid of moles. And we want to go where? What did we just say? Grams. We want grams of sodium chloride. Now, how do I find the number for that? I pull out my periodic table and I go, okay, sodium weighs this and chlorine weighs this. And together that gives me 58.44. And this conversion factor right here is relating grams to moles or moles to grams. So what is that conversion factor called? That is your molar mass. That's your molar mass for sodium chloride. This conversion factor right here is your concentration. Okay. All right, so moles of sodium chloride cancels out. You guys do this calculation, and what you're going to get is 3.46. Oops, a little ahead of myself there. 3.46 grams of sodium chloride. There's your answer right there. It has 3 sig figs. This value right here is 3 significant digits. This one right here, we don't count that. So the 1 liter looks like it might be 1 sig fig, but there are exactly 1,000 milliliters in exactly 1 liter. So that has infinite sig figs there, so we don't look at that one. This one right here has how many sig figs? You've got 3, and this one right here, there's 4. So what we want is 3 because we have 3 and 3 and 4. And you want to go with a lower number, so in your answer, you're going to have 3 sig figs. Okay, so how would you make that solution? Well, you'd measure out 3.46 grams of sodium chloride on the balance, and then you would put that 3.46 grams of sodium chloride into some kind of container that would allow you to measure 60 milliliters. So we don't often see volumetric flasks that are 60 milliliters. Usually they come in 50 milliliters or 100 milliliters or 250, 500 or 1 liter. So you might have to use a different measuring device like in the picture below. So you can see in the picture below, we have a graduated cylinder. Now, you can use a graduated cylinder to make this solution, but it's less accurate than your volumetric flask. So just so you know there. All right, so number 4 says calculate the molarity of the following ammonium dichromate solution. So ammonium dichromate has this big old formula right there. Okay. So looking at this, it tells us that we have 90 grams of ammonium dichromate. So let's go ahead and turn that into moles because remember, molarity is moles over liters. So we need the mole component. So we have 90 grams of ammonium dichromate. And we need to get to moles for that. So we're going to write grams of ammonium dichromate on the bottom here, and we're going to write 1 mole of ammonium dichromate on the top there. Now, where do I find the number that goes in the denominator? Well, you pull out your periodic table and you go, oh my goodness, there are a lot of atoms to add up here. I need 2 nitrogens, 8 hydrogens, 2 chromiums, and 7 oxygens. Ah! And you're just going to trust me when I say that it's 252.07 grams of ammonium dichromate for every 1 mole of ammonium dichromate. All right, we're going to do the calculation for that. And we're going to get 0.357 moles of ammonium dichromate. Now, take a look at the picture here, and what you'll notice is that you have 250 milliliters of deionized water measured out in that graduated cylinder there. But the second picture shows you that you did not put the full 250 milliliters of DI water into your volumetric flask here, that you had some left over. And that's because your ammonium dichromate is taking up some space. Okay, so see, this is also a 250 ml. So you go ahead and you put your DI water in with the ammonium dichromate, swirl it, put some more, and then you're going to fill it up to the mark so that you have 250 milliliters of solution. So you did not put 250 milliliters of solvent in there. It makes 250 milliliters of solution. And we have to change 250 milliliters to liters because we're looking for the molarity, which is moles over liters. So we have to get rid of milliliters and go to liters. And like always, we have how many milliliters per every 1 liter? We have 1,000 milliliters per liter, or 1 liter per every 1,000 milliliters. And that is going to give us 0.250 liters. So we're going to take our volume and we're going to take our moles and we're going to put them together to figure out the concentration of this ammonium dichromate solution that we just made. So which number goes on top, 0.250 or 0.375? 0.375 because it's got the mole with it. So we have 0.357. Did I say 0.375? I meant 0.357. 0.357 moles of ammonium dichromate divided by 0.250 liters. Both of them have 3 sig figs. And what that is going to do is give us 1.43 mole per liter ammonium dichromate, which translates into 1.43 big M for molarity, which we say as molar ammonium dichromate. And you would not put ADC on the label because that's just my abbreviation for ammonium dichromate, because I did not want to write it out every time. So if the bottle were to be labeled, it would say ammonium dichromate, or it would have the formula written out so there would be no confusion as to what the chemical was in that bottle. And we'd say we've got a 1.43 molar ammonium dichromate solution there. All right, my friends, that is calculation for molarity and how to make solutions. We're going to go on in the next slides to do some of the other concentration units. But for now, we are done. Bye-bye.